Hello and welcome back once again. So in the previous lecture, we discussed about wrought and cast aluminium alloys. And with regard to the cast alloys, we started discussing about this aluminium silicon alloys, which are an important class of aluminium alloys finding applications in various industries because of their favorable properties. Okay, so we talked about some of the aspects of these aluminium silicon alloys, and in this lecture today we are going to continue on this, and there are a few more things that we are going to cover today in this particular lecture. So in case of these hypoeutectic alloys, some of the important alloys, we can see some examples. For example, this 356 aluminium that you have, this is a very commonly used aluminium cast alloys. And here, if you see the composition, it is basically aluminium 7 silicon and some amount of magnesium. And you can further improve the strength of this alloy by heat treatment, because as I said before, this is a heat treatable alloy which will form this kind of precipitates, and this will lead to precipitation hardening and improve the strength. Precipitation hardening we are going to take up separately later on and talk about it in more detail as to what happens, what is the precipitation sequence and so on for all the heat treatable alloys that we have. Then you have another alloy which goes by this designation 333, and this has about 9 silicon and some copper. One more is 332, which is having about 9.5% silicon, about 3 copper, and some amount of magnesium also. Okay, so castability, as I said, is one property that is really very good in these alloys. But apart from that, you also have good corrosion resistance. So these are some of the other properties. Their weldability is also good. And of course, it's a low density light material. With a density less than pure aluminium, because silicon also is a lighter metal only. And property wise, if you see, there is something to do with this silicon phase that you see over here. This is present like a completely different phase which is distributed all over the place. So this will give rise to a particular property which is really very useful for some of the applications that I was mentioning, particularly for the automotive, right? In the engine block, for example, what is the property that you need? What is the main property that you need in the engine block? If you think how the engine works. So if it is a 4-cylinder engine, there are 4 cylinders, right? This block will have 4 cylinders. What is there inside the cylinders? There are pistons, okay, and these are movable parts, isn't it? The piston continuously moves up and down, and that is how the engine runs, right? So that tells you that there is a lot of friction inside this block in the cylinders, right? So here we are looking for a property which is resistant against friction or wear, right? So what is that property that we are looking for here, which is resistant against friction and wear? What property we are talking about which will resist wear and tear when there is high friction? You simply need a hard material, that's all, and that is how the cast irons are also used, right? So as I said in the beginning, it is a cast iron equivalent, not only in terms of the castability, but also some of the properties, okay? And again, silicon comes into picture for that as well. The presence of silicon in this particular morphology provides the material a very high hardness, which is useful for this kind of applications, right? Even if you talk about the other application that I was mentioning for the automotive, that is the wheel, right? Does it need resistance against friction and wear? It does, right? And it is continuously rotating. It is all the time rotating whenever the car moves, right? So there also you need a material which is resistant against wear and tear, and therefore you need a material which should have high hardness, okay? So the silicon phase, as I said, is the one which will provide that particular property, and that is why these kind of alloys are so commonly used in those applications, particularly in automotive, okay? So these are some of the hypoeutectic alloys, and this is what you will see in the microstructure: the alpha aluminium phase and the eutectic silicon, okay? And many times you might find this eutectic silicon along the grain boundaries or the interdendritic regions if you have dendrites, right? So these are cast alloys, and you can expect that this kind of dendrites will form once the casting is solidified, right? Because dendritic structure is one of the most common microstructure in case of castings. So here also it is no different. You might find this kind of dendrites as you see over here, and this eutectic silicon will be along the interdendritic regions, which are actually the grain boundaries, okay? Now, if you look at the hyper, where you have more than 12% or the eutectic alloy around 12.6% silicon, then as you see from here, like here you have the alpha aluminium. Here the additional solid phase is going to be this silicon itself, what is known as primary silicon, okay? So apart from this eutectic, you will have this primary silicon particles, like how you had this alpha aluminium along with the eutectic in case of the hypoeutectic, right? So now if you come to the right hand side, on the hypereutectic side, you have this primary silicon in this two-phase region here, liquid plus the silicon, right? So that will continue to remain in the final microstructure. So if you look at the microstructure, you will find these primary silicon particles like this, blocky particles that you see, along with the eutectic that you can identify now because you have already seen how the eutectic looks like. So this is your eutectic over here, right? But apart from that, you also have this primary silicon particles being present. In this case, unlike the previous one, where silicon is only in the form of the eutectic and there is no primary silicon in this case, okay, when it is hypoeutectic, right? So this also tells you, because of the presence of these additional silicon particles, the hypereutectic alloys are going to be much harder compared to the hypo ones, okay? But the one problem that you might face in this case, again due to the presence of this kind of morphology for the primary silicon, is the reduction in the ductility, okay? So if you look at some of the alloys in this category, we have 390. This alloy has 17% silicon, some copper and some amount of magnesium. So as I said, this is having much higher hardness, and therefore this can be used for the pistons also, because it can resist wear and tear because of the high hardness. And other application that you can think of for this particular alloy is in air conditioning compressors. AC compressors. There also it finds some application. Okay. Now the question is, if we want to avoid this kind of morphologies, as I was telling you before, it is possible to change the morphology and come up with a morphology like this, where it is no more flaky or no more blocky kind of morphology, rather it is more uniform and fibrous, as we call it, because this is going to give you this kind of microstructure is going to give you much better properties compared to this kind of microstructure where you have blocky or flaky kind of silicon. Okay, so it can be modified, as I said, but how to do that, that is the question right now. So as I mentioned, you can have different ways to modify this microstructure, and one of them, as I mentioned, is by some additions in minor quantities, like for example barium can be added, and similar other elements such as strontium and sodium can be added in very small quantities, which can lead to this modification. Okay, but we need to understand as to what happens when you add this kind of elements, that too in small quantities like this, such a minor quantity. What exactly happens that suddenly changes this kind of flaky morphology to this kind of fibrous one. Okay, so if you want to understand that, you will have to look at what happens during the solidification as the solid continues to grow, and how the phases grow during the solidification. Okay, so we need to understand that in order to understand as to what is the mechanism of this modification when you add this kind of modifiers. Okay, so in order to understand, you have to start with the structure of silicon, because here we are talking about the silicon phase only. So if you want to understand how silicon would grow during the solidification of these alloys, you have to first understand what is the structure of silicon, and if there is any preferential growth direction for silicon to grow when the alloy is solidified. Okay, so silicon, you might know that has this kind of covalent bonding, where each silicon atom is bonded to 4 others, as you could see from this particular image over here, right? And in terms of the atomic bonding, if you see, this will form a tetrahedron, right? Because each of the silicon atoms, let's say this one, if you see, it is bonded to 4 others, and if you join these 4 atoms, okay, they will be located at the vertices of a tetrahedron. Right, so it's a tetrahedral kind of structure that silicon has. Okay, in terms of the atomic arrangement, if you see. Okay, now when the silicon is growing during the solidification of the aluminium silicon alloys, you need at least two of these tetrahedra to form a stable nucleus for the silicon phase. Okay, the silicon phase that you have in the eutectic. That means I am talking about the eutectic reaction as it happens during the solidification, as you cool the alloy from the molten state. Okay, so you need at least two of these units, two of the tetrahedra to form a stable nucleus of the silicon, and then as you pull it down more and more, this is going to grow. Okay, but the question is how this is going to grow, whether it will grow uniformly in all direction, or will it have a particular preferential direction and take up a particular morphology due to that, right? So what we have seen that it does take up a particular morphology by growing in a particular direction, as you could see. So that tells you that when it grows, unmodified, this is going to grow in a particular direction only, right? And that is why you see those kind of flecks. Okay. So if you go to the next slides, that is what is being shown here as to what is that preferential direction in which the silicon will grow. Okay. So this is a model which was proposed based upon some experiments on growth of silicon. So this theory goes by the name TPRE, which stands for twin plane reentrant edge. Okay, so this TPRE stands for that. So this mechanism tells you that when the silicon grows, twinning occurs, as you could see over here. Okay, so twinning is a kind of crystal defect, or a mechanism of deformation in metals, which leads to formation of a plane across which the lattice become a mirror image of each other. Okay, so this twinning plane, if you see, on either side of that particular plane, the lattice in terms of the atomic arrangement is a mirror image of each other. Okay, so you can consider that if you have a twinning over here, so this is like a plane, and across this, if you look at the atomic arrangement, this side will be a mirror image of the other side. Okay, so that is what is known as twinning. Okay, now for this growth mechanism to take place, it says that you need at least two twins to form for the continuous growth of the silicon dendrite in a particular direction. And what is that direction? That direction is this 2-1-1 directions. It can be any combinations like 1-1-2, 2-1-1, and so on. So the preferential direction for the silicon to grow is the 1-1-2 or 2-1-1 directions. And as I said, for this to happen, you need at least two twins. Okay, like what you have in this particular figure over here. Okay, so you have a twin over here, okay, between A and B, and then one more again coming here along the 1-1-1 planes. Okay, so why there is a need for two twins for the silicon to grow, that you can understand from this particular image over here. So when you have two twins coming together, it will take up a structure like this. Okay, so where if you see this in terms of the 3D image, the 3D structure, it will look like this. So here are the two twins that you see over here, this and this one. So here you have here and here. Okay, so these are the two twins that you have for the silicon to grow, and it is growing in this particular direction. Okay, so it is like coming out of the plane of the paper. Okay, along this direction. So that's your 2-1-1 direction. Now, as I was saying, for this growth to occur preferentially in this particular direction, and for it to continue, for the growth to continue, one twin is not enough, because if you have a single twin and if it grows, it will lead to closure of the twin, as you could see. So this is in the beginning, and if it grows in this particular direction, in 2 1 1 direction, then ultimately, since it is growing along this direction, you can understand that these edges that you have, these edges are going to close. Okay, so that will form a ridge kind of thing, and you will have no more of this kind of edges, and therefore this twin is going to close like this, taking a trigonal kind of geometry. Right? So that is why if you have a single twin, this growth will stop, and you will not have the continuous growth of the silicon in that particular direction. Okay? So that is why for the growth to continue, you need two twins, as you can see from here and here. Okay? So now consider this scenario where you have those two twins, at least minimum two twins. And here is the edge that the twin forms, which we call as the reentrant edge. Okay, so that kind of forms a particular angle that you can see. Here the angle is 141, that is the corner that it forms. And then it also forms a ridge like this. Okay, so this is the reentrant edge, that you have, which kind of becomes a preferential sites for the further growth to occur, because this becomes a preferential nucleation site, meaning the atoms will prefer to attach along this edge compared to any other place in this crystal when it is growing. Okay, so that is why when the atoms get attached to this in this preferential nucleation site, more and more atoms will come and tend to attach to this when it is growing in this particular direction only, because in this particular direction, when the growth happens in this particular direction, then only you would have additional reentrant edges coming into the picture, and therefore providing more and more nucleation sites for the crystal to grow. Right? For example, if you take a look at the second image over here, it has already grown one more layer. Okay, so it was in the beginning, it was only this part. Okay, so now you have this growth which has already occurred now. Okay, and due to that, you can see there are additional reentrant edge, this one and two, this one and this one, which have come because of this growth in this particular direction. Right? So as you have more of these reentrant edges, more growth occurs, because, as I said, these reentrant edges are the preferential nucleation sites for more atoms of silicon to get attached and the crystal to grow. Okay, so as more and more atoms will come and attach to these edges, more growth will take place. Okay, and that is how this grows in a particular direction, and that is exactly why you see that kind of morphology like what you have seen here, right? This kind of flaky morphology, because it has grown in a particular direction. Okay, so let us try and summarize then. So if I want to summarize this mechanism, as I said, it is basically due to these twins which form during the growth of the silicon crystals. And if you have at least two twins, then it will lead to growth in a particular direction, which will introduce more of these reentrant edges. Okay, and these are the sites, these reentrant edges are the sites where the atoms can preferentially attach, meaning these are the preferential nucleation sites for the silicon crystal to grow. Okay, so as it grows in this particular direction, it introduces more of these reentrant edges, and that is how it leads to a growth into this particular direction. Okay, and that is why you have a flaky kind of or a needle kind of morphology in unmodified aluminium silicon alloys. Right, so this was about the growth. Now the next part was how to prevent this growth, right? Because we do not want, in many cases, this kind of morphology in the microstructure, right? So the next question would be as to how do you prevent this growth, and what can be done to modify this kind of flakes to a fibrous kind of morphology, which might give you better properties, right? So that is the next part that we are going to discuss. So before we wind up, let us have a look what we have learned today and take a summary. We primarily talked about the cast alloys, okay, and we also understood the different designations of cast alloy. Here, unlike the rod alloys, we have 3 digits to specify that designation, like 1XX, 2XX, and so on. And apart from that, you also may have a decimal point and a digit followed by that. So that decimal point can either be 0 and 1. 0 indicates it's a cast alloy, and if it is 0.1, that would indicate that it is an ingot. So it kind of tells you what is the product form when it is cast, either in the casting form of the kind of product shape that you need, or it is in the form of an ingot. Okay. Then we took the example of this particular alloy to discuss more about the cast aluminium alloys, because this alloy is one of the most commonly used aluminium alloys because of its excellent properties, which are useful in many applications such as automotive. Okay, so in these alloys we have talked about the phase diagram, the aluminium silicon phase diagram, and we have seen that it basically is a eutectic phase diagram where you have a eutectic at 12.6% silicon and 577 degrees Celsius. Then we talked about both hypoeutectic and hypereutectic aluminium silicon alloys in terms of the microstructure and some of the examples, including their properties and so on. So here you have, apart from the eutectic silicon, you may also have the alpha aluminium in case of the hypoeutectic alloys. Some of the examples of this: 333, 356. 356 is one of the very commonly used alloys. Then we also talked about the hypereutectic aluminium silicon alloys, wherein apart from the eutectic silicon, you also have primary silicon in terms of this kind of blocky particles. Okay, and some examples of these alloy are this. For example, this 390, which is 17 silicon and some amount of copper and magnesium, and this kind of alloy finds applications in pistons and air-conditioned compressors. And then we talked about the growth mechanism of silicon as to why it grows in a particular direction. And we can understand that with the help of this theory known as TPRE theory or TPRE mechanism, which talks about growth in a particular direction. Okay. So with the help of that, we could understand as to why silicon takes this kind of morphology, or why this directional growth occurs in aluminium silicon alloys. And with that, we come to the end of this lecture. Thank you for your attention.